In the previous video, we talked about how to use backpropagation to compute the derivatives of your cost function. In this video, I want to quickly tell you about one implementational detail of unrolling your parameters from matrices into vectors, which we'll need in order to use the advanced optimization routines. Concretely, let's say you've implemented a cost function that takes as input your parameters theta and returns the cost function and returns derivatives. Then you can pass this to an advanced optimization algorithm like fmin-unc, and fmin-unc isn't the only one, by the way. There are also other advanced optimization algorithms, but what all of them do is take as input a pointer to the cost function and some initial value of theta. These routines assume that theta and the initial value of theta, that these are parameter vectors, maybe Rn or Rn plus 1, but that these are vectors. And it also assumes that your cost function will return as a second return value this gradient, which is also like Rn or Rn plus 1, so also a vector. This worked fine when we were using logistic regression, but now that we're using a neural network, our parameters are no longer vectors, but instead there are these matrices, where for a 4-layer neural network we would have parameter matrices theta 1, theta 2, theta 3 that we might represent in octave as these matrices theta 1, theta 2, theta 3. And similarly, these gradient terms that we're expected to return, well, in the previous video we showed how to compute these gradient matrices, which was capital D1, capital D2, capital D3, which we might represent in octave as matrices D1, D2, D3. In this video, I want to quickly tell you about the idea of how to take these matrices and unroll them into vectors so that they end up being in a format suitable for passing into as theta here or for getting out for a gradient there. Concretely, let's say we have a neural network with one input layer with 10 units, a hidden layer with 10 units, and one output layer with just 1 unit. So S1 is the number of units in layer 1, S2 is the number of units in layer 2, and S3 is the number of units in layer 3. In this case, the dimension of your matrices theta and d are going to be given by these expressions. So for example, theta 1 is going to be a 10 by 11 matrix, and so on. So in octave, if you want to convert between these matrices and vectors, what you can do is take your theta 1, theta 2, theta 3 and write this piece of code, and this will take all the elements of your 3 theta matrices. You can take all the elements of theta 1, all the elements of theta 2, all the elements of theta 3, and unroll them and put all the elements into a big long vector, which is theta vec. And similarly, the second command would take all of your D matrices and unroll them into a big long vector and call it dvec. And finally, if you want to go back from the vector representations to the matrix representations, what you do to get back theta 1, say, is take theta vec and pull out the first 110 elements. So theta 1 has 110 elements because it's a 10 by 11 matrix. So that pulls out the first 110 elements, and then you can use the reshape command to reshape this back into theta 1. And similarly, to get back theta 2, you pull out the next 110 elements and reshape it. And for theta 3, you pull out the final 11 elements and run reshape to get back theta 3. Here's a quick octave demo of that process. So for this example, let's set theta 1 equal to be ones of 10 by 11. This is a matrix of all ones, and just to make this easier to see, let's set that to be 2 times ones 10 by 11, and let's set theta 3 equals 3 times ones of 1 by 11. So this is 3 separate matrices, theta 1, theta 2, theta 3. If I want to put all of these into a vector, I've set theta vec equals theta 1 semicolon theta 2 theta 3, right, there's a colon in the middle, and like so. And now theta vec is going to be a very long vector. There's 231 elements. If I display it, I find that there's this very long vector with all the elements of the first matrix, all the elements of the second matrix, then all the elements of the third matrix. And if I want to get back my original matrices, I can do reshape theta vec. Let's pull out the first 110 elements and reshape that into a 10 by 11 matrix, and this gives me back theta 1. And if I then pull out the next 110 elements, so that's indices 111 to 220, I get back all of my 2's, and if I go from 221 up to the last element, which is element 231, and reshape to 1 by 11, I get back theta 3. To make this process really concrete, here's how we use the unrolling idea to implement our learning algorithm. Let's say that you have some initial value of the parameters theta 1, theta 2, theta 3. What we're going to do is take these and unroll them into a long vector we're going to call initial theta to pass into f min unc as this initial setting of the parameters theta. The other thing we need to do is implement the cost function. Here's my implementation of the cost function. The cost function is going to give its input theta vec, which is going to be all of my parameter vectors that in a form that's been unrolled into a vector. So the first thing I'm going to do is I'm going to use theta vec, and I'm going to use the reshape function. So I pull out elements from theta vec and use reshape to get back my original parameter matrices theta 1, theta 2, theta 3. So these are going to be matrices that I'm going to get. So that gives me a more convenient form in which to use these matrices so that I can run forward propagation and back propagation to compute my derivatives and to compute my cost function j of theta. And finally, I can then take my derivatives and unroll them, sort of keeping the elements in the same ordering as I did when I unrolled my thetas. But I'm going to unroll d1, d2, d3 to get gradient vec, which is now what my cost function can return. It can return a vector of these derivatives. So hopefully you now have a good sense of how to convert back and forth between the matrix representation of the parameters versus the vector representation of the parameters. The advantage of the matrix representation is that when your parameters are stored as matrices, it's more convenient when you're doing forward propagation and back propagation, and it's easier when your parameters are stored as matrices to take advantage of the sort of vectorized implementations. Whereas in contrast, the advantage of the vector representation, when you have like theta vec or d vec, is that when you're using the advanced optimization algorithms, those algorithms tend to assume that you have all of your parameters unrolled into a big long vector. And so with what we just went through, hopefully you can now quickly convert between the two as needed.